AQIS and AICTE approved. Invite for the session Mr. Yogendra Singh for the image classification of using convolutional neural network and its implementation. So I would like to introduce Yogendra sir. Yogendra sir is a co-founder and the director at Fox Technologies and Fox Coding School. He has several years of experience with leading companies like Qualcomm, Mango, and Z-Drive. While working with these companies, he has played a strategic and a key role in deploying hundreds of applications successfully. Sir was part of the team that deployed a framework for low and middle tier mobile devices that enable developers to quickly create nice mobile applications and user experience. So, sir has a rich experience of Python, machine learning, deep learning, and we can learn any program related queries with sir also. So, I would like to welcome Yogendra sir for the session. Sir, please.
Thank you, Pooja ma'am. And uh, please confirm me in the chat window, Pooja ma'am. Am I audible to you so that I can start with?
Yes, sir, you are audible.
Okay, thank you. So, a very good morning to all of the participants in this faculty development program organized by Poornima and sponsored by AICTE, as I'm being told. So today, I'm going to have two sessions basically. The first session that we are just starting now, and in the second session as well, immediately followed by the first one. So what is the agenda, first of all, right? So what is the agenda for today? As per the schedule, everybody knows that now in this session, we are going to talk about how we can implement a CNN model that can work as an image classifier. Okay, and let me share my screen with you. So I'll just use some sketchboard so that explanation becomes easy at my end. So let me start the presentation. So as a disclaimer, I do not have a presentation, a slide, and I would be using a sketch board here. And along with that, for the code implementation, we will have some, a coding part as well. Now, as you can see on my screen, that agenda is basically a CNN implementation for image classification. And when you talk about image classification, it's a kind of an act where you want to classify the input image, whether it's a image of a cat or whether it's an image of a dog, let's say, for example, right? So in the image, you just have to, give a kind of a prediction whether it is a cat or whether it's a dog. And you only have the two classes, let's say, then it becomes kind of a binary classification. And in a couple of cases, I'm directly jumping because now I have seen the schedule. A lot of speakers have already, gone through the basic part of the deep learning or CNN or RNN or ANN, a couple of things in the deep learning part. So whenever you talk about image classification, I'll keep the discussion in two kind of mode. One mode would be how you can classify a a black and white image or a grayscale image. So I will talk about how you can handle a black and white image classification using CNN. So that is the one part of that entire session. And the other would be that how you can handle a colored image, a data set So colored image data set for some kind of classification, obviously. So this is also there, but I will take this colored image classification activity in the second session, and there itself we'll also understand the concept of transfer learning, that how you can use a pre-trained model for your image classification. So my requirement is my personal requirement, right? And I want to meet that requirement, maybe the client's requirement as well. And for that purpose, I'm not going to train my model. Rather than I would go for a way where I can use a pre-trained model. And using a pre-trained model, that means someone else has trained the model, and you are just using those learnings to get a classification for your requirement. That kind of activity is basically known as transfer learning. So we'll understand that part, that how transfer learning can be implemented, how you can use the transfer learning for your research area, for your implementation of something related to this image, right? And obviously, before I come to, because both of the kind of implementation parts are there, right? In this black and white image classification, I would use a very popular data set that is MNIST data set, right? So I'll talk about the MNIST data set when we come to this part. Before that, I'll put a quick, a walkthrough on the basics of CNN, right? So we'll understand. I'm sure that a lot of people have already gone through this. So can I have a feedback from all the faculty members who are in this meeting room that with respect to this FDP, I was going through the schedule. So is basic of the CNN like covered in the previous sessions? Can someone confirm me to that? Or maybe Pooja ma'am?
Yes, sir. Yes, sir.
Okay.
In last session, ma'am has covered the idea how the CNN works and neural
Okay.
network working.
Okay. So that is easy for me then, right? Thank you. Now, basics of CNN. So I'll quickly go through that part. Thanks, Ankita ma'am. She says yes, sir, covered. Now, in this, we'll set some background. So moving from academic understanding and coming to applied side of that, it would be easy journey for us. And then we'll make a one switch from this to this as well, where you have already a kind of a cleaned data set that can be used for image classification. But this discussion would be pretty much close to the real requirement. So I have what I have done. I have basically taken a use case we recently did for one of the client. It is not covering the entire requirement specs, but one part of that I have taken, so that you can understand that how transfer learning or the CNN a kind of concepts can be used in the real scenarios. So I'll talk about that. So this is the basic agenda. And I think first session will get over by 1:15, and then we'll have the second session from 2 p.m. onwards. So let's start with the understanding on around CNN. So first of all, where we see the CNN is fitting in this entire ecosystem, I think first we need to understand that part. And to understand where you see the CNN, I think it's a good idea that you should have a look on the deep learning, right? And now everybody knows, at least in this group, right, that deep learning can be seen into two subcategories, where one kind of deep learning can be seen as a supervised deep learning, right? So this is a supervised deep learning, and the other part is unsupervised deep learning. And when you say supervised deep learning, right, the term is coming from the supervised machine learning and unsupervised machine learning only. And when you say supervised part, that means the kind of problem right, you are dealing with, or kind of the data you are dealing with, the composition of the data is like that, that it has, a set of features, and obviously along with the features it has a label as well, right? So labels are also there. Okay, so if the data set has both features and the label, then it is called as labeled data set. You call it as a labeled data set, and in case of labeled data set only, you can have a kind of predictions, maybe in form of a regression, maybe in a form of a classification, but obviously the prediction can happen only in the supervised domain, maybe supervised deep learning, or maybe supervised machine learning as well. Now, in supervised deep learning, primarily researchers are focused on the three architecture. They are primarily focused on three architectures. The one which is called as a basic building block of any a deep learning architecture or a deep learning system, that is ANN. And now whenever someone says neural network, basically you are referring to ANN, right? And ANN is like artificial neural network, right? That is a kind of artificial neural network. And whenever people talk about neural network, they are talking about a computer architecture that processes the data in a certain fashion, and that fashion is basically a kind of a layered architecture, right? So now we understand that part as well. It's a layered architecture to process the data, and in that layered architecture, now you are well aware that what is input layer, what is output layer, what is hidden layer. A hidden layer can be more than one as well, but it would be one. It would be one, but it can be more than one as well, right? Even the number of hidden layers decide that how deep your neural network is. Like if you have 100 hidden layers, you can easily understand that it is going to be a complex deep learning model, right? The more the number of hidden layers you have, it becomes more complex. And sometimes, we have seen that if you add more hidden layers, you get into a problem of overfitting sometimes, right? So it is, a kind of a hit and trial mechanism, that what should be the right number of hidden layers in your system, right? So depends on the problem, basically. Now, after understanding this, that what the layered architecture is, you must have gone through one more concept, that that every layer, whether it's a input layer, whether it's a output layer, whether it's a hidden layer, every layer has a collection of a node, right? Every layer has nodes inside it. And whenever we say node is basically in a basic literature, people call it as a perceptron, but the node is a basic elementary processing unit that is part of the neural network, and every node has this kind of details, like it has an input, then it has a output, then it has a weight, and it has a bias, and then it has a activation function as well associated with a node, right? So activation function is also there. And now how come all of these things are related to each other? So your output is always something like that, where you you take input and multiply it with the weight, and then add bias to it, and this entire value is passed to activation function. I'm taking AF. AF means activation function, a short form, just so that is AF. And so this is how your things are there inside the layer. And there is also a study which tells you that how many nodes you need in the input layer, right? I'm taking it a little fast because I'm not putting too much details, but I'm just covering, giving a touch to what the concept. So now there is a study, and everybody knows this fact, that how you decide that how many nodes you need in the input layer. And this should be clear to everybody, that the number of nodes in the input layer is something which is based on the data, right? If your data has n number of features, right, it will have n number of nodes in the input layer, right? So, and corresponding to, let's say, image data. So corresponding to image data, every pixel works as one feature, right? Every pixel works as a one feature. So let's say if you have an image of 20 by 20, now we know that it has 400 pixels, right? That means every pixel is working as a feature, and if it has 400 pixels, obviously you need 400 nodes in input layer whenever you are implementing a neural network for that, right? So kind of that. Now, output layer number of nodes is also based on the problem. Like you must be clear that in case of regression, you only just need one node in the output layer, and for binary classification as well, you can you can use just one node. But in case of a multi-class classification, you need the number of nodes just equal to a number of classes in the problem statement or in the data set. So can you please confirm everybody that are these things I think already covered in the previous session? So I can just take a liberty to quickly move to the next a part of this walkthrough. And can you please confirm? So you can use chat option there, right? You have, or maybe if someone is interested to speak, maybe he can speak or she can speak. Okay, so this was our ANN part. That was our ANN. And ANN is basically the basic building block of any neural network. Okay. The second architecture that is very much popular right now is CNN. And CNN basically stands for convolutional neural network, right? This is standing for convolutional neural network. Okay, and the third architecture is known as RNN, which is called as recurrent neural network. Okay, now coming to this CNN part, right, where we call this as a convolutional neural network. Mostly, the CNN is used for a kind of computer vision, right? And whenever you say computer vision, it can be object detection, it can be a object identification, it can be a face detection, it can be a face recognition, it can be a case where you are trying to read the text that is in the image. Maybe you're trying to understand the green light or red light kind of in a given image or in a video feed as well, right? So a lot of these things what I'm talking about, they belong to computer vision, right? And whenever you upload a image on let's say Facebook, you get a prompt that do you want to tag this friend, do you want to tag this friend, do you want to tag this friend. That is all computer vision and basically implemented using CNN model, right? Now, all of those things are implemented using a CNN model. And I'll give more focus on the CNN part, but first let me talk about this RNN. When we say RNN, that is recurrent neural network, and how come this is different from ANN and CNN? Basically, neither ANN nor CNN has a memory component, right? They don't remember what was the output in the last activity, for example, right? They don't have any memory component as such. They don't remember anything, right? And they only give the prediction based on the current input only, right? They give you the prediction based on the current input only, not what happened in the previous activity of making a prediction. But RNN has a memory component, right? So RNN has a memory component, and it is one of the best architecture to capture a pattern in a long series of data. And that's why whenever you you say time series data analysis, the time series data analysis is well handled through a RNN network, right? And a time series analysis. If you say example of RNN, where RNN is being used in almost daily life, we are using it, and almost everybody has a account on Gmail, right? So everybody is using Gmail services, and whenever you go to draft the mail, right? Whenever you go to draft a mail, and whatever you start writing, right, you start getting the suggestions there, right? It can be a one-word suggestion, it can be a full sentence suggestion as well. All of that is happening through this feature of RNN. So RNN is basically handling that, because whatever you have written so far, right? So it is basically keeping a track using the memory component, that what you have written, not only this, what you have recently written, but what you have written in the past, right? So then only it will make a sense that you get a good kind of a suggestion here. So it is a perfect example of a RNN, right? It is a perfect example of a RNN. Now, whether you are using CNN or whether you are using a RNN, your ultimate decision comes from ANN only, right? So first you need to deploy ANN, and later on you need to go for ANN, because ultimately, right? So using ANN, what you can perform regression as well, and you can perform classification as well. So to perform regression or classification, ultimately you need ANN. So even though you are using CNN, but CNN has got a different purpose. We'll understand that purpose now. But ultimately, whatever you get as an output from the CNN box, right, that will work as a input to your ANN, and then it will give you a classification. Let's say the image has a cat or image has a dog, kind of a decision. Similarly, the same works with the RNN as well, that whatever you get as a data, you need ANN after that as well, right? You need ANN as well. That will give you the regression or something like that. Okay, particularly in time series analysis, RNN, then you have a ANN, because that ANN would be used to perform regression, not classification in this case. But I have seen a couple of a kind of research areas where people have been clubbing CNN and RNN together, right? So what they do first, that if they have a long time series data, first they will feed it to CNN, and the CNN makes a kind of a compression of the data, or basically it does a kind of a dimension reduction. So once that reduced data, or a kind of a compressed data, goes to RNN. So that way you can basically save some kind of a processing, because if you directly feed your time series data with a large volume to RNN model, it may take a long time to process. But if you apply CNN on that, there may be a reduction in the size, and after the reduction, you can pass on that time series data again to RNN, and then obviously you will need ANN as well to finally make a prediction. So here you have all these three, right? In case of time series analysis, you can apply CNN followed by RNN, and then obviously in the last you have an ANN part as well. So kind of, I don't know. I have not gone through much papers, but in the industry, people have applied such pipelines. So now coming to a little details on the CNN part. So here we have this CNN. Okay. Now, what we are discussing, we are discussing that CNN is used for image classification, right? And CNN can be used for processing the video feeds as well, because ultimately a video is a collection of frames only, collection of the images only. The CNN is exactly doing what? Let's understand this part. CNN is kind of a feature extractor. Okay, it works as a feature extractor. Okay, and ultimately, how you position the CNN in the current scenario is like that you give a input image, for example, right? So this is your input image. Okay, and now this input image will go to a CNN. Okay, and CNN is ultimately extracting the features from this image data, right? So it will give you the extracted features, right? And those extracted features again go to your ANN model, and where you get a classification. So here you get a classification, whether it's a cat or whether it's a dog. Okay, this is how a CNN is used to extract the features from your image. So this is kind of a way, right, that can give you features from an image. But in a sense that deep learning models or machine learning models are recently, they have become very popular. They were there, from 50s, 60s, 70s, right? Machine learning algorithms were there, even deep learning concepts were there, everything was there. But because of lack of computation, lack of memory storage, right, it was too expensive. It was, these algorithms were not giving the accurate results, right? And that's why people were a little hesitant that out of research area, nobody was using them, right? And a very, a less applied side of, a scenario was coming up. But because of, because now computation is easily available, power is easily available, memory has no issues, because now we have a cloud services, and even our handheld devices are so powerful, right, that they can handle large amount of data. They have good computational capabilities. So implementing any machine learning algorithm or feature or deep learning feature has become damn easy now. And that's why whether you apply linear regression, whether you apply KNN or k-means or something else, now it has become easy. Then what was the case earlier? Recently, CNN has become a kind of a de facto standard for image processing. That's fine. Okay, got it, right? But what was earlier? What was the story, right? So earlier, how people were doing the image classifications, we should understand that part. Earlier, how come people were using image classification or image processing kind of activities? So exactly what they were doing in the earlier scenario. So now let's say you have an image. So I'm talking about the earlier scenario now, not the current one, not in reference to CNN. The reference to CNN, this was there, right? Now you have an image. So this is your image data. Okay. Now this image was given to certain algorithms, right? And those algorithms were, extracting the features. And those algorithms, if you remember, like kind of SIRT or SURF, these are kind of algorithms. They're still existing, right? You can do a Google around that. So exactly these algorithms were, getting a feature extracted from the image. So features were extracted here. Okay. And once these features were extracted, right, this data, obviously, whenever you say features extracted, obviously label is also there, right? Now this entire data, right, will work as a training data set for machine learning algorithms which can perform classification for you, right? And now that in case of machine learning, the algorithms that you use for classification are logistic regression, right? ML classification I'm talking about. So logistic regression is one of the algorithms that can be used for a classification. The KNN is also there, naive Bayes is also there, right? A lot of algorithms are there. You can use SV M, basically support vector machine, and we use SVC, in particular image support vector classifier. Out of these, algorithms for classification, this SVM works best on image data. This SVM works on the image data. And when I say image data, I'm talking about this extracted features data that has been extracted using a CERT or SURF kind of algorithms, right? And now you feed this data to your SVM model, okay? And that SVM model will get trained and give you a classification, whether it's a cat or whether it's a dog. So that was the earlier story, okay? So that was earlier story. Researchers were doing the image classification and using this fashion. But now, because of the CNN, right, arrival, now people have shifted to this model where your, a CNN and ANN, right? CNN and ANN is working as a black box, and it automatically, extracts the features from your image data and finally giving you a prediction whether it's a cat and dog. So you don't have to focus on this part that you deploy a third-party algorithm or a third-party application that can extract the features, and then you will use your machine learning model like SVM or something else to make a classification on the data. No, now it is taking care of everything. So we have got a replacement here, guys. We have got a replacement we are not using anymore, right? So this is how a CNN and ANN clubs together are used for image classification purpose. And now we little bit zoom out this a portion that how exactly CNN works. So CNN inside the CNN, now we know that CNN is a feature extractor, right? What is CNN? CNN is an architecture that can be used to extract the features from a given image. Okay, now how the feature extraction happens, okay, how the feature extraction happens, that we need to understand. So let me go into certain details that how exactly feature extraction happens. So the CNN has 4 major steps inside it, right? CNN, whenever you say CNN, convolutional neural network, it has 4 steps inside it. The first step is obviously a mathematical operation, and that process is known as convolution, okay? So that is there, and from that activity, you get a name, convolutional neural network. There, that is there. So once you have a convolution applied, whatever output you get after this convolution, you apply your activation function on that, and that activation function is ReLU here. And now you understand what the ReLU is. Basically, ReLU is only doing a very simple stuff. If your data input, right, if your input is less than or equal to 0, your output is always 0, right? Your output is 0. And if you have input greater than 0, your output is as it is as input, right? So your output is this. So this is kind of your ReLU feed. So you must have gone through a couple of activation functions or transfer a function where you have like ReLU, or for example a sigmoid, or a softmax kind of activation functions, or tanh, right, hypertangent, and other activation functions or transfer functions are there, but we are going to use ReLU here. And in the third step, that is called as max pooling. That activity is called as max pooling. Okay, and after the max pooling, you apply a process that is called as flattening. That is called as flattening. Okay, and whatever response you get after this flattening, it goes to your ANN. So whatever response you get after the flattening, it goes to your ANN, and this is how things happen. Okay, one more thing, in the CNN, right, you can have multiple iterations of convolution, ReLU, max pooling. So you can have one convolution, one ReLU, and one max pooling, and then again you can have a convolution, ReLU, max pooling. Again you can have convolution, ReLU, and max pooling. Again you can have a convolution, ReLU, and max pooling. Convolution, ReLU, and max pooling, right? Convolution, ReLU, max pooling. Convolution, ReLU, max pooling, kind of that. And finally, right, you flatten your data, You flatten your data, that will fed to your ANN model. So this is how this is, right? So if you see that how the convolution is taking place, or how the railway is taking place, or how the max pooling is taking place, and how you flatten, the flattening of the data means converting a two-dimensional data or a three-dimensional data into one dimension. That is known as flattening, right? So you are just kind of doing a reshaping on the data. Data is reshaped from 3D to 1D or 2D to 1D kind of stuff. That is known as flattening. So ANN receives the data in one-dimensional format. That is the purpose of that flattening. And now, if we talk about that, how exactly these steps are taking place. So here we have a kind of, see, this is our kind of an image that can be used to understand the convolution. That can be used to understand the convolution. And basically, convolution is a mathematical operation where some operation is performed on your input image, right? On your input image, and this input image is basically convoluted, right? This input image is basically convoluted with a data, and that data is kind of a matrix data. And this matrix data is basically called as a filter or a kernel. We call it as a filter, or we call it as a kernel. Okay, and here you can see the operation in terms of example, that your image is a colored image that you can see here, and that's why that image has been shown into 3 layers, right? And what these numbers are representing? These numbers are representing the pixel values. So let's say the first pixel is what? The first pixel of the image, because it's a colored image, right? So the first pixel of the image is like where the red component is 4, right? The green component is written here, and the blue component is written here. So all these, 3 components will make one pixel for you. The first pixel in the image, right? And then you have a second pixel whose R component is this, then G component is this, and then B component is this, and that way. So as of now in the example, we are only getting the values. We are only seeing the values in the first layer. That layer represents all of the pixel components corresponding to red, right? And then you have this green layer, and then you have the blue, because every pixel is made of what? R, G, and B, right? RGB format is there. That is there. Now how we are going to convolute this input data, this input image, with these filters. So these filters are nothing. They are a kind of a, they can be seen as a matrix data of 3 by 3. In current example, you are seeing that, this is a matrix of 3 by 3. And if you have 3 layers in the input image, right, obviously a color image, then you need 3 filters, right? Then you need 3 filters. Why you need 3 filters? Because one filter would be convoluted with the red component. The another filter would be convoluted with the green layer, and the this last filter would be convoluted with the green. So here we can see that how come the convolution is taking place. As of now, you can see we have got some predefined values in this filter. Okay, so predefined values in the filters are 1, 0, -1, 1, 0, -1, 1, 0, -1. And obviously the values in the other layers are also there. And now how the convolution will take place? The convolution of the red layer will happen with this red layer in the filter. The convolution of the green will happen with the green, and the convolution with the blue will happen with the blue layer of the filter, right? And how the convolution is taking place, that is very interesting to know. So maybe you can see this layer which is seen in the red color is overlay on this input data, right? We are just making an overlay of this data on this one, right? And once you make an overlay, how the operation is taking place, In that operation, in that convolution, this 4, which is the pixel value of the red component, right, from the first pixel, so 4 is getting multiplied with 1. Correspondingly, 9 getting multiplied with 0, and the 2 with -1, and 5 with this one, 6 with this 0, 2 with this -1, 2 with this one, 4 with this 0, and 5 with this -1, right? And whatever output you get, right, because you will multiply and then you will add everything, right, then it becomes your the red component convolution part. And similarly, the same operation taking place with the green layer and the blue layer, and then we need to add all the components. So we have got the red component, right, we have got the convolution from green component, and we have got the convolution from the blue as well. All of these finally added, right? So you can consider that that will give you an intermediate data, this will give you intermediate data, this will give you intermediate data, and then only after adding all these 3 intermediate components, you make the final pixel that would be written into the image as the output image, right? So here you write the next, the first pixel. And then what you do, guys, you shift this, a window, which is kind of an overlay, right? Overlay of our filter to the right. And we shift it to by 1 pixel, right? And then now it will cover 925, 624, 45, something like that. And then we again perform the convolution and get the next value, and then gets the next value, and so on. And once your first row is complete, you shift this window by 1 pixel. So now it will cover 562, 245, and 565. Let me show you one kind of animation may help you in this regard. So just a minute. I'm just showing you one animation probably. Okay, so here you can see in this web page, a very famous web page by Satosa. Here you can see a kind of a visual, way that how the convolution is taking place, right? How the convolution is taking place. For example, see, we have a filter, right? We have a kernel filter. I was talking about this filter, right? This filter I was talking about. So we have a filter, right, in this. And that filter is having certain values, like, can you see? This is a 3x3 filter. In couple of cases, you can have a 5x filter as well. You can have a 7x7 or 11x11. This is not fixed. But for understanding purpose, we are taking that it is a 3x3 filter. Okay, now here you can see this filter has fixed values: 0, -1, 0, -1, 5, -1, 0, -1, 0. So this is the metric, that is the kernel, that is the filter, and this filter would be used to perform the convolution, okay, on the input image. And in this example, we have an input image. This is our input image, okay, that you can see. This is our input image. And as of now, this input image is obviously a black and white image. It's not a colored image, right? It's a black and white image. And now that means if it is a black and white image or a grayscale image, that means it has only just one layer. It has only just one layer, right? Otherwise, if it would have been a colored image, it would have been 3 layers. But as of now, to understand, we have only just one layer, okay? And now we have, can you see? So we have, see this, we have certain pixels, values. So can you see? I'm using a net kind of, this, object is there, which is in the size of 3x3. Why 3x3? Because that is our filter size, right? And now can you see, if I take this net on the, top left corner, you will see the corresponding pixel values in that image. So in the first row, you are getting the first pixel as 206. In the first row, the second pixel is 205. In the first row, the third pixel is 247. In the second row, the first pixel is 244, and then 161, and then 137. And then in the third row, the first pixel is 192 and 154 and 75. And then here you can see how the convolution is taking place. This 206, which is the first pixel in the first row, is getting multiplied with your first value in the kernel, right? First value. And what was the first value in the kernel? That you can see it is 0, right? So it is getting multiplied 0. There you can see in middle of two images, right? 206 getting multiplied with 0, then 205 getting multiplied with -1, 247 with 0, 244 with -1, and so on, right? So this is your first output, 65, and that 65 you can see in the output image on the left side as a small red square that you can see. So that is the output, right? And now if we shift it by 1, I'm shifting my net by 1, right? So here you can see I'm shifting, right? And if I shift, there is a change in the pixel values, right? And then there is a change in the output. And similarly, so now this is kind of a scanning going on, right? It's a kind of scanning, and this is the convolution is taking place. So finally we are done with the first row. Then now what we'll do, we'll go back again, but shift our convoluter by 1 pixel, right? This shifting is known as stride, right? So in this particular case, stride is just 1 pixel. In couple of cases, people take a stride by 2 pixels. So in that case, what will happen? The starting point is this, and then the next operation will happen from here, because we have shifted by 2 pixels, because the stride was 2 now. But in normal cases, people take a stride by 1 pixel. So that is, so now it will again, go this way. So there, we complete. So it's a kind of a scanning, if you can see, right? The first row, and then second, and then second. So this is how the convolution is taking place in a black and white image, right? In a black and white image. And now, what is very, very important to know regarding the CNN, guys? Can you see? This is the same principle which is applied in your any mobile application which is related to your image, right? And in that application, you will see even in your gallery of your smartphone, right? You go and select any image, and you apply a lot of filters on that, right? You apply a lot of, maybe you convert your colored image to a black and white, maybe you convert your image to an embossing effect, maybe you convert your image to sharpen, maybe you convert your images to something else, right? So a lot of filters are there. Basically, that a filter is a convolution process on, right? So you apply so many filters, right? You are using Snapchat or WeChat, or a couple of other applications, right? That is a convolution is only applied, and then you get the final output, because you can choose the corresponding filter, and that corresponding filter is basically applying the convolution, and then it gives you the idea. And now here you can see that based on what you want to do. If you want to do sharpen the image, you have certain values in the filter. If you want to blur the image, then you have different set of data. If you want to let's say emboss the so you have something else. So you have different values in your filter, different values in your a matrix or kernel, right? And in that filter is basically does a convolution for you. Okay. Now coming to a very important discussion, and that is kind of a crux of the CNN, right? That is a kind of a crux in the CNN. What is that? In my example, that animation I was using, right? You understood that it was an input image, right? It was your input image, and it has a lot of pixels into that, right? And I was getting convoluted this with a 3x3 filter, right? 3x3 filter, and this 3x3 filter has certain values. Let's say -1, 0, -1, 0, -1, 0. A kind of I'm just taking some random numbers, right? So this was the case, and then you were getting the output. Okay. But in case of please everybody understand, that is very important. That is the only crux of the CNN. In case of CNN, what happens, right? When you apply a CNN, this is your input image, right? This is your input image, okay? And this input image would be convoluted with a filter, right? With a kernel. This kernel has, again, let's say a 3x3 size. So it is 3x3, okay? Now, CNN in the beginning, right, will initialize the values in a random fashion, okay? So in my example of the animation, I was already taking some predefined values. Predefined values for sharpen the data, predefined values for blur the data, predefined values for something else, embossing for this. So, whatever the number of effects you want to have, correspondingly, you can have so many values in each filter, right? Now, in a case of CNN, please, you have to understand this philosophy that in the beginning, all of these, numbers which you see in the filter, these numbers are basically called as weights. So all of these weights are randomly initialized. All of these weights are randomly initialized. Okay, and the convolution happens, and then this, extracted feature part, right? Extracted feature part goes to ANN, and then ANN will make a prediction, and let's say it says cat. Okay, and now this prediction would be compared with the actual output, because we need to see, right, whether it's a good prediction or whether it's a bad prediction, right? So in the training phase, this is what happens, right? You feed some data, convolution will happen, features would be extracted, that will go to the ANN, and then you will get a prediction. And now this prediction is not matching the right out, the target, right? And in the actually this input image is of dog, for example. So what will happen now? The back propagation will happen, obviously, and that will do what? That will update our weights, right? That will update our weights. It will update the weights in the ANN, as well as it will update the weights in the kernel. And now, because of the back propagation, you start getting the weights updated in your kernel as well. And finally, once the training is complete, your model is going the right predictions to you. In a way, now what you have done, you have got the optimized values in your kernel, right? You have got the optimized values in your kernel, and these optimized values can now directly be used in the testing, right, for any unseen input image. And now the convolution will happen to get a final prediction. And in that case, it is a testing. And in the testing, you're not updating the weights, right? Because the updates of the weight has already happened during the back propagation and the training part. So this is how a kernel, this is how a filter will get the final values in the beginning, right? In the beginning, in that example, we already have these predefined values, right? But in actually, how come we get these values, right? These values are, got during the training part and during the back propagation, right? So this is how that back propagation activity will actually, optimize the weights in your filter. And once that optimization is done, your training part is done, and now you can use that model in the deployment, and you can use that in your testing activities for any unseen input data. That was the crux of the CNN, right? That was the crux of the CNN. So I hope I have covered the, kind of a philosophy that someone should be knowing if someone putting, some efforts to learn CNN. So please give me a kind of a feedback that is that clear with everyone. So then I'll go to some implementation part now, and I'll take you through a code where we have we'll understand some problem statement. हम एक किसी problem के through उसको समझेंगे कि how you can use CNN for your image classification, obviously. So Kaliba, okay, Sayyidi Abraham Kaliba is saying clear. Ankita Jain saying yes sir, clear. Professor Manoj Devakar is there saying clear. Thank you. So yeah, Saila, CNN is only a supervised deep learning part, right? CNN is only a supervised deep learning part. So CNN or RNN, they are the architectures used in supervised only, not in unsupervised way. Now, let's take an example, that how you can implement a, for example, a CNN in your lab or in your research project or any implementation. So let's understand that part. regarding the, regarding the tool and technology, right? So we understand the academic side of that, and now we want to make a, a use case to understand that how things are getting applied. So let's see a applied view of this now. So now we are making a transition from academics to applied side. Okay. And in the academic section, what we're talking about, we were talking about what the ANN is, what the CNN is, right? What the RNN is, right? And what are the various steps like convolution, ReLU, then max pooling, and then flattening in the CNN, right? And how the things are happening in that. Now for the implementation, you need to use certain tools and technologies, right? Tools and technologies which can be used to implement your project or research, right? As of now, in the industry or even in the kind of academia, uh, Python has become kind of the most popular programming language for this. Okay, but that doesn't mean that Python is the only way you can do the things. But as of now, if you talk about the popularity and the new project implementations, so Python has become the most popular programming language. And even from Stack Overflow survey, right? Stack Overflow survey 2019, which is a very, very popular site among developers community in the world. In 2019 survey, the Python was at the #1 position in terms of popularity. So that was there. Now, Python is only the way you can write a code, right, to implement something. But along with the Python, here we need a couple of libraries. We need a couple of libraries, and basically these libraries or frameworks, right? Couple of libraries and frameworks are the implementations of the algorithms, right? They are the implementations of the algorithms, right? Let me say an example for this, that all of the faculty members, you are already aware that in your second year or in the third year of the curriculum, you teach data structures or algorithm kind of subjects to students, right? And whenever you say data structures and algorithm, you have a very a popular topic that is called as, for example, sorting. Okay, the sorting is there. And in the sorting, what you teach people, teach these students, you teach that once you have unordered data, right? You have unordered data, you can apply certain algorithms, right? That will give you output as sorted data, right? And now you have a lot of algorithms here which can be used to sort the data. You can have merge, you can have a quick sort, you can have bubble sort, you can have insertion sort, you can have selection sort, and so many sortings are available there. And based on the situation, you can apply. And what you teach to these students, you teach to students that how you can implement a merge algorithm in the code. Then the people write the code in C programming or C++ or Java or maybe in Python, right? This is, and now once that code has been implemented, and let's say you save that a code in .c or in .h format, header file, right? And what will happen in that case? Now anyone can use, right? Anyone can use this source code, right, to sort the data, right? And now the guy who is using this header file, he does not need to care what is written inside, because inside the implementation has been written, and I just only need to use that and see how it is doing on my data, right? And if you don't want to implement these algorithms, right? If you don't want to implement these algorithms, our C compiler, particularly GCC compiler, right, gives you inbuilt function, right? It gives you a function called qshort, right? And basically that qshort function is the implementation of quicksort only. And you can directly use qshort in your problem solving, right? And you don't need to look exactly how the quicksort is working, right? Similarly, right, whenever we say any supervised machine learning algorithm, let's say linear regression or decision tree or random forest or classification algorithm like KNN or naive Bayes or SVM or any other algorithm, right? We have a couple of libraries in the industry. So popular libraries are sklearn, right? Sklearn is there. Sometimes people call it as scikit-learn as well, right? Scikit-learn. So this is a library which has all of the implementations available, right? Which has all of the implementations available, and you can directly use those algorithms to solve your problems, right? That is for classical machine learning, problems. Classical machine learning problems means logistic regression, linear regression, KNN, k-means, a priori, those algorithms, right? Now, for deep learning implementations, we have a couple of libraries. So now I will focus on the deep learning part. For deep learning, there is a very popular library from Google, which is open source. Keras is one of them. Keras is the open source library. And the second library is TensorFlow. Okay, so TensorFlow is also there. And as such, both of these libraries are from Google, but behind the scene, Keras uses TensorFlow backend only. That means Keras does not have its own capabilities in terms of implementing something, right? Keras has been used as a wrapper library that makes easy to write the code activity, right? The coding becomes very easy in Keras as compared to TensorFlow. But whenever you use Keras, ultimately in the end, it is using TensorFlow only, right? So the real implementation lies with TensorFlow, not with the Keras. The third, the library, so both of these are from Google, right? So both of these are from Google. The third library, which is popular as such, is a PyTorch, right? Which is from Facebook and Uber, right? That is from Uber. So even other libraries are also there, like MXNet and something like that. So a couple of that. Okay. Now these are Keras or TensorFlow kind of libraries. So in our implementations, we are going to use Keras. Okay. Now for computer, so these are generic libraries, right? These are generic libraries. People have specifically designed other libraries as well, and they are used for computer vision. Okay, they are used for computer vision. So along with these libraries, maybe you can use a OpenCV, again a library. CV stands for computer vision. OpenCV library can be used for face detection, face recognition kind of stuff, right? And the second library that is also quite popular, YOLO, is also there. I think the second version is available now. So YOLO 2, people are calling it. So OpenCV, YOLO, and other libraries, if you Google, you will find hell lot of libraries for that. Now, this is how you can use OpenCV and YOLO as well. And what is good about OpenCV, you can use OpenCV even on the microcontrollers like Raspberry Pi and all that, right? So using a Keras or a TensorFlow may become a difficult, and that's why you have another version called TensorFlow Lite. A TensorFlow Lite, which is a light version. Okay, TensorFlow Lite, which is a lightweight version of the TensorFlow. The TensorFlow Lite can be used and it can be integrated into a mobile application, let's say Android app or iOS app, or on a IoT application which is running on let's say Raspberry, right? So TensorFlow Lite can be used there rather than using this heavyweight TensorFlow original version. Google has a separate version for such development activities. So we are going to use Keras as of now. So let's move to that part now. So what we are going to do. So let's see that. So let's remove this plot. Okay. So just a minute. Yeah. Now, for the implementation purpose, right? What the problem we are going to take? Let's understand that problem first. So the problem that we are going to take is a amnest data. Okay, so what the amnest data is, I will talk about that. So the amnest data set. So we are going to use a amnest data set, and that amnest data set has, basically it's an image data set. And in the amnest data set, you have around 60,000 images for training purpose and around 10,000 images for testing purpose. Okay, so let's focus on what the amnest data set is. So we have amnest data set, and here you can see I'm on the Wikipedia page, right? So let me click on this amnest data set, and let's see what this database is. Amnest database or data set. It is a large database of handwritten digits, right? Handwritten digits, and that can be used for training various image processing systems. So we'll use this data set, right? And here you can see, people are using in the machine learning and all, and it has 60,000 training images and 10,000 testing images, and every image has a label as well, right? Every image is a label. So here you can see, if I click on this image, right, what we have in the data set, we have these images, right? So these all are handwritten images. So someone writes 0 this way, other one will write the 0 this way, other one will write the 0 this way. So this is one guy. So maybe we say Pooja ma'am that please write from 0 to 9. So Pooja ma'am writes 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9 this way. And then we ask someone else, maybe Deepak sir, so he will write with this way. And so everybody has his own handwriting, right? So people will write in different ways, so everybody has a different style to write the numbers. So this way they have gone to 60,000 people, and they have written in such way, and now these images are used for training, right? And 60,000 training, 10,000 testing images, and every image is of a particular size. Every image is a fixed size. Can you see? Every image is of a 28 by 20 pixel. It is a black and white, grayscale images, right? All of these are the grayscale images. They are not colored images, right? So exactly what we need, what we need. So exactly something like that we can train our model, okay? So we can train our CNN model. So the story is like this, that now we have to have our own CNN model, okay? And we will use these 60,000 images, okay, to train the model, okay? And now after training the model, if we give an image, let's say using my handwriting, and I write 2 like this, right? Using my handwriting, I write 2 like this. So what should I do? I should be able to get a prediction that what has been written in this image, right? What has been written in this image. So it should give me a prediction that you have written 2 into that image, right? So this is my a requirement, that I need to create a model, and after that I need to basically train that model, and then it should be able to so let's say for example, we have animation here. The link is maybe I'll share with you. So this is giving me an option where I can draw something, right? So here I can draw something. So let's say I draw something probably 2 here. So let's see. My system is a little slow somehow. So let's refresh it. Probably that will help us. Okay. Okay. So here I write 2, and then you can see this was our input image, right? The input image is there. Then we have a convolution, right? So then we have a convolution. And currently the system has applied 6 different type of convolutions that you can see. Can you see? This is one convolution, this is another, this is one is another, this one is another, this one is another. So it is using 6 filters that you can see as of now, right? And then you have a max pooling, right? And then again you have again a convolution layer, and then you again have a max pooling approach, right? And then you have finally it is giving you a prediction 2, right? So if I come from that CNN part, quickly I can also talk about that was our first activity of the convolution. After the convolution, we apply a ReLU on that, right? So after that, that was the second activity. You missed, I think, that discussion. So in the second step of the CNN, we apply a ReLU. ReLU is just converting your negative pixels to 0. That's it, right? Because of the convolution, it may happen that some of the pixels in the output image are negative, right? We just put them to 0. That's it. That was the ReLU. And in the third step, what exactly we do? We do a max pooling approach. So we do a max pooling approach in the second step that was there. So let's say this is the image after the ReLU has applied. So we have applied the convolution, we have applied the ReLU, and this is our input image after the 2 steps. And now we are going to apply a max pooling on that. So exactly what the max pooling is. In the max pooling, generally we take a window of 2 by 2, right? And in that window, we pick only the pixel with the maximum value. So can you see? We are taking a 2 by 2 window here, and we are picking only the maximum pixel value. Okay, here is the catch that why you are picking the max value pixel only, because if you think in terms of mathematics, right, the most prominent feature in the image will have a higher pixel value, right? The features which are sharp, right? The features which are prominent, right? The features which are sharp, they will get the value in a higher, so you will get a pixel value as higher compared to others, right? And that's why to only pick the meaningful features, to only pick the features which are really important to make a decision, right? You just retain that one and you leave the others, right? And that's why you can see that out of this collection of 12, 28, and 12, we are picking the maximum pixel value 20. Then you shift that 2 by 2 window by a stride of 2. Now we are taking a stride of 2 that you can see. So now you pick the maximum pixel value, and here as well you are picking the maximum pixel value 112, and then you are picking the maximum value 37. So this is how a max pooling happens. And now here is one more philosophy that you need to understand, that max pooling is also kind of a dimension reduction. Can you see? Earlier our image is 4 by 4, but now it has become 2 by 2. Why it has become 2 by 2? Because we are only retaining the prominent features and leaving rest of the features, because anyway they are not going to help you in the decision making, whether it's a cat or whether it's a dog, right? And that's why you are doing a max pooling into that. And as a last activity, what was the last activity? As a last activity, we are kind of doing a flattening of the data. So that is the flattening of the data. So let's say this is your output image after max pooling. So what you have done? You have done convolution, you have applied ReLU, you have applied max pooling, and now you want to flatten. So let's say this image is 3 by 3. So what will happen? You just convert from 2 dimension to 1 dimension. So this is this. Okay? And now you can think that this is the first pixel, this is second pixel, the third, fourth, and so on. Now this first pixel, will go to the first node in the input layer. The second pixel will go to the second node in the input layer. The third pixel will go to the third, a node in this, right? So here you can see that if you have so many pixels, so 1, 2, 3, 4, 5, 6, 7, 8, and 9. So if you have 9 pixels, and our image was 3 by 3, right? So if you have 9 pixels, how many nodes you will need in the input layer? Can you respond to that query? If we have 9 pixels after flattening, right? How many nodes we will need here? We will need obviously 9 nodes in the input layer. Yes, thank you Ankita ma'am, and thank you Ashutosh Kumavati. So they have responded. So that's it. So ये चीज हमारी convolution में हुई है, और अब हम थोड़ा सा let's see in the code now. So we just need to close it. My system is getting a little heated up. Okay. So here we are back. So that was our AMNIST data introduction, and now exactly one more catch around the AMNIST is that this data set already comes in Keras. Okay, this data set already comes in Keras, not in the image format. Not in the image format. This database of AMNIST data, AMNIST images comes in the format of ND array. Okay, it comes in the format of a ND array. So that data is already there in our Keras. So we don't need to load it anywhere, right? We don't need to load it anywhere. We can directly get it from our Keras library. So that is how you start using it. So let's take a quick look on the implementation side. So here you can see we are importing the Keras, which is the library for our deep learning projects, and we want to implement a CNN model. And as of now, our focus is on implementing AMNIST data set, right? So that is there. And here you can see we are importing the Keras. So all the attendees, let me know that are you already familiar with this Google Colab? And I think you must have a session, something on Google Colab. I want to know from you that are you guys already familiar with the Google Colab? It's a cloud, and its the interface is very close to Jupyter Notebook. The interface is very similar to Jupyter Notebooks, and this is and the file that is being saved on the Google Colab is with extension IPYNB, which is interactive Python notebooks. Which is interactive Python notebooks. So Nivedita is saying yes. Dr. Ganeshwara Rao Mitta is saying yes. So I think people are already aware with the Colab now. So it's easy for me now. So in the first, you can see I'm just importing the Keras library is there. Okay. And after the import, so I'll just go through, I'll take a quick walk, and I'll share this code as well with Pooja ma'am. Maybe she can share with you. So this is the Keras, import of the Keras. Here you can see. So I'm just connecting. Here you can see we are connecting with the Google Colab here. And Colab comes with a GPU as well, right? It comes with TPU and GPUs and all. So it's a good tool as of now. People are using it for their deep learning projects. But if you want a paid version, it is free basically. And if you want better services, you may choose a paid model. So I think there are two very popular platforms are there which you can use. Obviously, you can use Amazon Web Services, AWS, and there is a we used in some project. I'm not very much sure which project it was, but we used a paper space. I think it was paper space was there for AI. So here you can see it's a it's a cloud ML AI and effortless GPU infrastructure. And I think there was one more which is used in the industry. People are using. Crashel is also there. Crashel. There are a lot of as of now, but Crashel is also there. Crashel for AI infra. Okay. So Brochure is also there. It comes with the deep learning capabilities and all. So that was there. So here we used this. So now we have imported the Keras, and now here you can see we are using this MNIST data, so we need to import it, and that's why you can see we are importing this data here, right? So we are importing it, and after the import, we are loading it. And here we have a direct capability. Just a minute, I just need to delete it. It's not required. So delete the sum. Okay. So here you can see we are using a method called mnis.load data. So when you call this load data method, it will load everything for you, the training data set as well, and the testing data set as well. And when you say training data set as well, that means the images and their corresponding label. Images and their corresponding label. Images and their corresponding label, right? So this is the training set where we have the image data in form of an ND array, right? And this the test data is there, right? So we have this part now, and here you can see it's getting downloaded, right? And once this is downloaded, now we need to take a look that what kind of data we have in the training and testing. So here you will see that when you say train underscore images dot shape, it will give you that how many images it has, right? So it is saying that it has got 60,000 images, and every image is of size 28 by 28, right? And we can get to know a particular image. So if you want to access a particular image, you need to use an index. So let's say we want to see that what image we have on the 0, and we want to see that what exactly kind of data it is holding, means kind of pixel data it has. So I just need to say this. So it will give me a pixel data. Here you can see. So it is giving me a pixel data, right? First row will have this data. So this way, it has. So this is the first row data, this is second row data, and this way you have all 28 rows and 28 columns. So if you say dot shape, you will know that every individual image is of size 28 by 28, right? And if we want to know that what is the label, right, in the training set, what is the label for image 0, because by just looking at the pixel values we don't know, right? We don't know what kind of date label it has, right? क्या लिखा हुआ है उस image में वो हमें नहीं पता. If you want to know क्या लिखा हुआ है, we need to go for labels, right? So train labels. So and then we need to use the same index what we were using here. So it says that your first image and that data set, it is a digit of number 5. It is a digit of number 5. So this is how you can explore. Okay, now to train the model using Keras CNN, we need to reshape these images, and the reshape is like that we need to tell that what is the depth of the image. We are telling that 28 is the width, we are telling that 28 is the height, but we are not telling that what is the depth, right? In case of a colored image, the depth of the image is 3, right? So in case of a colored image that you can see, the depth is 3, right? So this is first layer, the second layer, then the third layer. So depth is 3, and that's why here you can see, guys, the size is given like this: 6 by 6 by 3, right? So 6 height, 6 width, and 6 the number of columns you can say, or the depth, right? So this is 3. But in case of a black and white image, this has to be 1, because only one layer you have, right? So and that's why we need to reshape it. So we have reshaped it and then finally, as a pre-processing activity, we are not building the CNN yet. We are just playing with the data. We are just cleaning up the data and preparing the data for a model. So here we are doing what? We are doing kind of a feature scaling. And what is the feature scaling? The feature scaling is a process that is being used in machine learning and in the deep learning as well, where you bring the feature values in a similar range, right? Because what happens, any machine learning algorithm or deep learning algorithm works on the magnitude of the data, not on the unit of the data, right? So to bring everybody on the same range, every column on the same range, you need to perform a feature scaling And it can be a standard scaling, it can be a min-max scaling. So we are doing a feature scaling here where we are dividing every pixel value by 255. So it's a kind of a min-max scaling we have. So this is what we have done. So, and the final activity is a kind of a one-hot encoded representation of our label data, right? So one hot encoded representation of the label data is like this. So let me tell you what is the one hot encoded representation. So see this. As of now, all the faculty members, you know that in the label, right? In the label, only the values we have, only the categories or the classes we have, either it's a 0, either it's a 1, it's a 2, or it's a 3, or a 4, or a 5, or 6, or 7, or 8, or 9, right? यही तो label होंगे हर image के. They are the categories, right? These are the categories. So every image that we have in the training of 28 by 28, right? Every image has a certain label, and that label can be 0 or either 1 or either 2 or either 3. So these are the categories now. These are the classes, right? These are the classes. And to a better representation, what we need to do, we need to convert them to a one hot encoded representation. Okay, or sometimes we call them as a two categorical. So this two categorical means we have these categories and we need a one hot encoded representation. And how you represent them using one hot encoding, that is very simple. Basically, what you do, that how many unique classes you have. So we can see we have 10 unique classes from 0 to 9. So you create 10 new columns. So 1, 2, 3, then 4, then 5, then 6, then 7, then 8, and then 9, and then 10, right? And let's say you want to represent 5, right? Category 5 into a one hot encoded representation. So this column is for 0, this is 1, for this is 2, this is 3, this is 4, then 5, then 6, then 7, then 8, and then 9. So what will happen in the one hot encoded representation? If you're representing a category 5 in the one hot encoded representation, you use this column to mark 1, and rest of the values will become 0. The rest of the values. This data is representation of category 5. Okay, and let's say you write something like that 0, 0, and then 1, 0, 0, 0, 0, 0, 0. Can you respond that what would be represented by this one hot encoded representation? Which number it is representing as of now? Which class is being represented if I write something like that? 0, 0. Okay, so now Vincent. Now it is representing 2 basically, right? So this is how you have to convert your data, right? So we are doing now. So we have used 2 categorical. So here you can see we are converting our label, training label as well, and the task label. So this is how you finally done with your data preparation activity. And now we are making a CNN model here, right? So now we are using Keras. And basically how Keras works, let me give you a little idea around that. So Keras is working like that Keras gives you 2 ways to create a model. It gives you 2 ways to create a model. One way is known as creating a sequential model that most of the people are familiar with. The second way is known as functional API. Okay, so that is the second model. But in 99% of the cases, I have used this, a sequential model. In a very, rare kind of a extreme boundary condition, people are using a functional API model. And what is the sequential model? The sequential model is like that. It will give you a empty container. So this is known as sequential model. And inside this container, now you can keep on adding the new layers, right? And these layers are basically called as dance layers, So we call them as a dance layer, right? So this is the first layer, then the second layer, then the third layer, and fourth layer. So you can keep on adding the layers, and the output from this layer will go to this layer, then from this layer to this layer, and so on, then so on. So as of now, we are using a sequential model. So here you can see we have created an empty sequential model, and now we are adding the convolution layer to it. And the convolution layer that we are adding will perform convolution 2D, and we are having 32 filters there, 32 nodes are there, and every filter is of size 3 by 3, right? And then we are applying the activation function in this line only. I'm not doing the activation separately. And then I'm telling that my input data is 28 by 28 by 1, right? And here, this input shape that we are specifying, it is a clear indicator that all of our images, everybody please listen, all of our images are of size 28 by 28 by 28 1, right? But that is not the true story in case of real life. ये तो data अभी clean data था, right? But what happens when you meet some client problem? In client problem, the data the client shares with you, every image is of a different size. हर image का size अलग है. So how you can specify the size here? That is the one challenge, right? So we'll understand that part in the next session. So, but as of now, we are lucky here that all of the images are of the same size, so we don't need to do extra handling of that data. But in the real life example that I will take in the next session, here we have to deal this problem as well. We have to figure out that how we can handle that problem. So this is how you add a convolution layer. And then you have to apply next pooling, and your next pool window is of 2 by 2 size here, and then you apply a convolution. This time you have 16 units, and you have taken a filter size of 5 by 5 here, not 3 by 3. So you can change it, right? And this is in any way not a fixed way, right? ऐसा नहीं है कि आप 3 by 3 ले सकते हैं या 5 by 5 ले सकते हैं. It depends, right? What kind of accuracy or what kind of performance you are getting, and then you have the next pooling. So here you can see we have done convolution next pooling here, and one more time here, convolution and next pooling is here, right? And then finally we are flattening our data. Here you can see, and then once this flattening is done, we have to add the ANN as well, right? So we are adding a ANN as well, right? So we are adding ANN. So this one will work as a hidden layer that you can see. The output from the flattening layer will go as an input to this layer, and the output from this layer will come to this final output layer. And here you can see how many nodes we are adding in the final layer. In the final layer, we are adding 10 nodes. Why we are adding 10 nodes? The 10 nodes are because in the output layer, to perform a multi-class classification, how many nodes you should have? The number of nodes should be equal to number of classes. And in MNIST data, how many different labels, how many unique labels we have, how many unique categories we have? We have 10, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have, and that's why we are taking 10 nodes, and the activation is going softmax, because whenever you want to do a multi-class classification, don't apply sigmoid, you have to apply softmax. So this is how you are done with creation of your model. Now you can compile it and you can fit it, right? And after the fitting, maybe you can perform an evaluation, and to check how your model is working, good or bad, you need to use a confusion matrix. So uske through we can find out how things are working good or bad for us. So that was a मैं थोड़ा सा fast रहा हूँ in an implementation. थोड़ा सा time का issue भी था, but I think the code is very self-explanatory. So when it comes to your inbox, it would be easy for you to implement. You don't have to do anything. It is directly available database in the Keras, and the philosophy that someone need to understand is only this, that how you can create your own deep learning model. And if you know that how to use sequential class, how to use a dense layer class, and how to configure your CNN in terms of number of input, number of nodes in the input layer, hidden layer, output layer, which activation to apply, which optimizer to use, how to compile it, how to set the number of epochs, how to set the batch size. Those things, if are clear to you, making a neural network using Keras is damn easy, damn simple. So that was that is from my side in the first session. And now in the next session will come close to a real life scenario where we would be using colored images of different sizes, and we'll solve some real life problem. And how to do that, we'll understand that later on, but in the second session. And there also I will talk about how you can use a pre-trained model like VGC16 and apply a transfer learning approach for your own predictions on the data. Okay, so please, before I close for the first session, I need a feedback from you. Was it interesting for you? Was it time well used for you? So yes, you can use Scylla. The number of hidden layers is not a fixed. Number of node. Number of hidden layers is not fixed, right? So that is just a hidden trial, Scylla. And yes, you can use the TensorFlow playground for that, right? So that was there. So Ashutosh Kumawat, I did not get your question. Can you please repeat that? So why we use two activation function when we use require only softmax in particular case? Where you're talking about, I'm not getting that. Maybe we get a little time to discuss in the second session, because in the first session we had a lot of things around that. So I think you are talking about this. नहीं, ये तो hidden layer है आशुतोष, right? Output layer तो सिर्फ एक ही है और इसमें हम एक ही activation function use कर रहे हैं. We are only using softmax. That's it. Are you talking about this, आशुतोष? हाँ, वो तो आउटपुट लेयर में, क्योंकि हमारे पास 10 यूनिक कैटेगरीज थी और एक्टिवेशन तो सॉफ्टमैक्स ही लगेगा. मल्टी क्लास क्लासिफिकेशन है ना, सिग्मॉइड लगा सकते थे अगर बाइनरी होता तो, और अगर रिग्रेशन ही परफॉर्म करना था तो फिर किसी भी एक्टिवेशन की जरूरत ही नहीं होती. So
Okay. So
I am done, Pooja ma'am.
okay. Thank you, sir. I thank you all the participants also. So we again reconnect at 2 p.m. With Yogendra sir again, and with the more understanding of CNN and transfer learning. Thank you again, sir, for the informative session.
Thank you, ma'am.
All the participants for the lunch time, and I request you to connect at 2 p.m. Thank you.